Hello, this is a presentation for commercial process design from the University of Florida, EML3005, mechanical design. My name is Andrew Wysocki. My other group members are Ariel Calemczuk, Lazar, Ruben Parco, Robert Wallace. Our objective was to create an epoxy machine for a Japanese noodle company to insert into the production line for the manufacturing of 1 millimeter thick epoxy noodles. So the design constraints that were given by the company are that they want an epoxy feed rate of 5 meters per second, final epoxy thickness of 1 millimeter, epoxy width coming in to the rollers of 1 meter, and a conveyor belt height of 1 meter high, and a width of 1.5 meters. We have a radial load of 100 newtons per roller pressing against it, and a friction coefficient between the dough and the rollers of 0.2. Some of the design considerations we took into account were design dimensions, power requirements, gear train design, roller bearings, material selection, and failure criteria. Design approach, we first determined our power, selected the motor, selected roller radii, gear train layout, and angular velocity to match up proper torque required. We also selected bearings, and then overall we performed failure analysis on rollers, bearings, and gears. The motor that we selected was a 3-phase CIM motor with a speed of 500 revolutions per minute, providing 100 watts of power. Design specifications that we ultimately came up with was a roller radius 2 inches, roller width of 1.5 meters. The gear train that we have an input gear connected to an output gear, connected to another output gear. The output gears are located along the same axis as the rollers, and input gear is spinning at the same rate of the motor at 500 revolutions per minute, and the output gears, due to their smaller radii, are spinning at 940 revolutions per minute. Final assembly we have our motor connected to one of our output gears and to another output gear along the rollers, and there's bearings right along there. The DE Goodman criteria was used to perform shaft failure analysis. Two assumptions that we made were that the torque amplitude is equal to 0 and the mean moment reflected that shaft is also equal to 0. When we get that, we found out that our roller radii is quite a bit larger than necessary for failure requirements, giving us an infinite roller shaft life. For gear fatigue analysis, we assume that the gears are approximated 2 cylinders in contact, and the cylinders have diameters approximately equal to the gear diameter. And we use contact mechanics to perform the failure analysis. We selected for the gears and the rollers to have the same material properties. Stainless steel 420 with a modulus elasticity of 29 KSI, Block-on ratio 0.24, and ultimate yield strength of 294 and 147 KSI respectively. 2 different gears that we have large gear and small gear, each with a pitch of 6.19 teeth per inch. Large gear has 47 teeth, and the small gear has a 25. Basically what we found out was we had a maximum pressure of 152 psi being applied to the gears, and a maximum minimum shear stress of 45 and 0 psi respectively. We used the modified DE Goodman failure criteria, or modified Goodman failure criteria for gear life prediction, and we found out that we were operating down in this range, so we have an infinite gear life. The bearing analysis that we did were courtesy of SKF.com, and we selected deep groove ball bearings with a single row, and found out that their life is going to be 251,910 hours. So, in conclusion, we have gears that will have infinite life, rollers will have infinite life, and bearing life of 252,000 hours. That's it, and thank you for